Okay, so today we'll start lesson from chapter 5, and I don't like this writing here. And the assumption is you already watched lesson 5. In fact, I want to say that this coming Monday, maybe I write it in red, is our next meeting. We will, in our next meeting, cover lesson 6 and maybe 7. So during this weekend, please watch both of them. Okay, please watch both lesson 6 and lesson 7. Now, my plan is this. On Monday, we will discuss lesson 6 and lesson 7. On that Wednesday, we'll do one of the sample tests. Okay, one of the previous test one, such that by the end of week 5, hopefully, so next week is week 4, right? So week 4, we finish the material. Week 5, you can study on your own. Okay, and then week 6, we have a test. Okay, now, in this chapter 5, section 5.1, we will learn some basic and fundamentals about probability. In this, we will learn the notation, what are the probability numbers or what are not probability numbers. Like for example, number 9. This is from your textbook, the 5.1. Give me a second. So from this 5.1, we'll learn the foundation of probability. Number 9, why is the following not a probability model? One of the property in our probability is that probability of any event will be between 0 and 1. Okay, so now why is this not a probability model, or why is this table not a probability distribution? Well, because probability of green give us negative. Okay, that's what's wrong. Okay, probability of an event cannot be negative. Number 10, why is the following not a probability model? All of them between 0 to 1 here, so what's wrong? Let's try to add. When we add this total of probability, when we add this probability, okay, when we add them, I think we get 1.2. And that's what's wrong. Why? Probability of the sample space is equal to 1. In other words, the total probability cannot be more than 1. Okay, the total of probability cannot be more than 1. The total probability of all possible outcomes cannot be more than 1. Now, that's for number 10. Number 11, which of the following numbers could be the probability of an event? Let me enlarge this. Yeah, which of the following could be the probability of an event? Now we know probability of an event has to be between 0 and 1. Okay, so which of the following can be probability of an event? This one is okay, right? 1/2 is okay. 1/3 is also okay. I mean 3/3. Anything between 0 and 1. 2/3 is also okay. 0 also okay. Now 1.5 is more than 1, so no, that one is no. -1/4 is less than 0, that's a no. Now, with this said, then every time you compute the probability, then you know the answer for sure is wrong if the outcome, the probability is more than 1 or less than 0. Right away, I mean, you don't need to think hard. It must be wrong. Okay, because the probability must always be between 0 and 1. Okay. Now, number 14. In 7-card stud poker, a player is dealt 7 cards. The probability that the player is dealt 2 cards of the same value and 5 other cards of different values so that the player has a pair is 0.44. Now, explain what this probability means. If you play 7 cards start 100 times, will you be dealt a pair exactly 44 times? Why not? So let's explain this one first. This is the first one. What does it mean? What does it mean? Probability to have a pair is 0.44. Okay, now then what does this probability to be 0.44 means? It means if the game is done many times, not only 100 times, but many times, then the relative frequency of getting a pair is 0.44. Okay, that's what it means. Now, but Thomas, then why if I play 100 times, if you play this card, this start 100 times, will you get exactly 44 times a pair? The answer is no, that's not what it means. Okay, no. But we know not too far from 44 times. Because this 0.44 is the average. So it doesn't mean that if you played 100 times, then you will get exactly 44 times a pair. No, but it won't be too far from 44 times. In other words, when you play 100 times, you will not expect 90 of them pairs, even though that's possible. Okay, it's possible, but very unlikely. Okay, our expectation will be what? Well, it'll be around 44, maybe 43, maybe 40, okay, maybe 50. Okay, but once we say, oh, it happens 60 times, I start questioning it. You know, something not really right, like that. Okay, so probability is one way to we use this probability to do expectation later on. Now, number 16. Number 16. Suppose you roll a die 100 times and get 80 times. Based on this result, what is the estimated probability that the next roll results in 6? So, based on that, what is the probability that you will get 6 again in the next roll? Okay, what is that again? Now, based on relative frequency, based on the result, right? Based on that result, then the probability to get 6 in the next row will be 80 over 100. Okay. But you may say, but Thomas, if that die is a fair die, it's supposed to be 1 over 6, right? If that die is a fair die, yes, it's supposed to be 1/6. But there are two issues with the assumption that the die is a fair die. First one, nothing in this passage say that we base on that assumption that the die is fair. No. Instead, based on this result, which result? The result that they get 86 out of 86s out of 100 times. Okay. Second, and the more important one, if the probability to get a 6 is 1/6, then the result you have earlier will not be like this. Okay. If this die were fair, then we should question why the outcome becomes so many 6s. In other words, right, the assumption that this die is fair is not reliable. Okay. Now remember, in my lesson, I described that to compute a probability, there are three methods, not only three methods, 3 levels to compute probability. The first one is relative frequency. We use relative frequency if we already have the experiment. That's why we also call this empirical method. Okay. Now, of 3 levels of computing probability, empirical method is the strongest one. Why? Because it is based on experiment. Okay. Now, the second one is by theoretical approach, sometimes called classical, sometimes called not law of large number, sometimes called the assumption method, theoretical conventional. Okay, but that's based on assumption. Based on assumption. Okay, now if we don't have empirical result from experiment, then the second level, the next step is we try to make assumptions and predict and compute the probability. Okay, but once we have empirical result, once we have that empirical result, right, like in this case, when the die is rolled 100 times, 80 of them are 6s, then from there we say, well, the probability of getting 6 is 80/100, not 1/6, not 1/6. Okay, now I try to emphasize this because the third one is by subjective method. Okay, I want to emphasize this though. In statistics later on, especially toward the end, we are challenged with some claim, and we need to support, okay, to see the sample if the claim being supported or not. Okay, I believe in my lesson I brought up one illustration about how do you know that your boyfriend or your girlfriend actually love you? How do you know that? Is it based on what he or she says? Now that's subjective though. Okay, if you base on what that person say, that's subjective. Okay, if you base on what that person's doing to his or her parents, let's say mom or dad, maybe brothers, sisters, that could be theoretical. Oh, you know what? This person know what love means, right? Not just say it, but this person know what love means. But at the same time, what happens if that person always come late when you have appointment for dating? It's like, yes, you say that you love me, but you hardly come on time. You always have excuse. It's just like something not right all the time, most of the time. Okay, so it's one thing about you say, me as an instructor, I get this comment or claim a lot. Thomas, I'm a hardworking student. It's like, okay, so right, you're a hardworking student, but then you try to register my class at the end of the second week. That's contradiction there. Okay, you may be hardworking, but you are not hardworking as a student. You may be hardworking as somebody else, like employee, or as a mom, as a dad, maybe. But no, you are not a hardworking as a student. Okay, that's why that your study becomes not in the first priority or second or high enough in your priority list. Now, I'm not saying that person is wrong. Okay, it's just like that person make a wrong claim. Simply because you're a hardworking employee, mom, or dad, doesn't mean you will be a hardworking student. Okay, so we are talking about these are different topics here, and then suddenly you project your hardworking personality into you as a student also. But that's actually no, that's not true. It's not doable this way. Okay, I can be a very good instructor, but it doesn't mean I'm a good dad. It can be, and in fact, it's very likely because I'm a very good dad, I won't be a very good instructor. If I'm a very good dad, my children must be in much higher priority than my students. Okay, it's so hard to balance it, right? I hope it makes sense. I hope it makes sense. Now, number 18. A person can have one of four blood types, AB, or O. If a person is randomly selected, is the probability they have blood type A equal to 1/4? Now, this requires some extra knowledge, and the answer is no. Okay, I happen to be a volunteer for American Red Cross and also donate platelets. My family have history of cancer, okay, such that one way for me to give forward, okay, pay forward to the help that my family got in the past, I donate platelets also, even though in the last couple months I don't do that anymore due to the pandemic, okay, but I donate blood. I donated blood. So, and platelets. So I know that, no, it's not 1/4. Okay. In fact, as I know, uh, I have that somewhere in my old test, the breakdown. Like if you have type A, what percent, type B, what percent, type C. There's no such thing, type C. A, B, and then type O. The most one as I know is either, I think type O is the most one. Yeah, I'm as of type B plus. Yeah, my wife A plus. Okay. Now, of course, if you look at a family, right? If you look at a family, you don't expect that in one family you have A and B, and A, B, and O. Very hardly happen. Very hardly happen. Okay, very hardly happen. Yeah, my dad has O, my mom have B. Okay, so you don't expect any children have A. Once you know any children have A, something not right with this person, or maybe to the mom or to the dad. I don't know. Something happened in the past. Okay, but that's genetic, right? That's genetic. In other words, no. Simply because it has four possible outcomes doesn't mean they must be equally likely. Okay, let me say that explanation. Okay, no, simply because it has four outcomes, it doesn't mean it will be equally likely. Okay, it doesn't mean like it doesn't mean each one of them have the same outcome. One very good example, very fast example for that is the probability of you hit a yellow light in an intersection. Okay, we have green, yellow, and red. Right? There are three outcomes, but you know that the probability of you get a yellow right at the traffic light is not necessarily 1/3. Okay, most of the time red. Do you know that? Yeah, most of the time red. In fact, more than, as far as I know, more than half of the time is actually red. Yeah, especially if you have a very busy intersection, then most of the time it's red. Okay, why? Because it is possible you in that intersection, even though we have like only this cross street, right? But then in a big intersection, if you are on this side here, then the green light may be one of them, the one turning left, right? So it's not only green and yellow and red for you. You may get red because they need to allow the car from the other side, right? Okay, but you may still get red if you have somebody from across the street needs to turn left. Okay, so if you pay attention, that actually most of the time, especially at the big intersection, you will get red. Okay, now the good news is that is not really the case in local streets, right? Where we don't have traffic light. Okay, so you may have stop signs only, right? Okay, now let's see number 20. This one is more difficult. If a basketball player shoots 3 free throws, describe the sample space of possible outcomes using S for a made free throw. I believe that S stands for success. And F for a missed free throw. I believe that F stands for fail. That success in making the free throw, then F in failing to make the free throw. The thing is, what are the possible outcomes? So what are the sample space? Okay, it's possible that all of them successes, right? Now, toward the end of this chapter 5, we will learn to compute how many possible outcomes if you do 3 free throws. Okay, but let's do it this way first. So either all 3 of them success, or the last one fail, or one fail in the middle, or success, fail, fail, or fail, success, success, fail, success, fail, 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 success, fail, fail, fail. These are all 8 possible outcomes. Now you can see it this way. You can see it this way. If I try to draw the tree diagram, okay, when you throw it first time, it's either you make it or you don't make it. Now, for each possible outcomes in the first throw, okay, when you throw it the second time, either you make it or you don't make it. Either you make it or you don't make it. Okay, now you see that at the end of your second throw, you have 4 possible outcomes. Right now, when you throw it again, for each possible pair you have earlier, either you make it or you don't make it. Either you make it or you don't make it. Either you make it or you don't make it. Either you make it or you don't make it. Okay, that's the tree. Okay, That's for number 20. This is another loop for number 20. Number 22, according to the American Veterinary Medical Association, the proportion of households owning a dog is 0.372. What is the probability that a randomly selected household owns a dog? The proportion of owning a dog is the same, therefore, to the probability of selecting a household owning a dog. That proportion will tell us the probability. Okay, that's for number 22. Let's see number 23 to number 26. We will learn to use further notation here. Okay, from number 23 to number 26, let the sample space be S equals to number 1, 2, 3, 4, up to 10. Suppose the outcomes are equally likely. Now there are 10 outcomes here. If they are equally likely, what is the probability of having one? Probability of getting 1 will be 1 over 10, right? Probability of getting 6 is also 1 over 10. Probability of getting 10 is also 1 over 10. Why? Because equally likely. Each one of them has the same probability. So, number 23, what is the probability of getting E? That is the event of getting 1 or 2 or 3. There are 3 outcomes there, right? Okay, so the probability to get any one of those 3 is 3 out of 10. It's getting 1 or 2 or 3. Number 24, what is the probability of getting event F? That is either you get 3 or 5 or 9 or 10. There are 4 out of 10 possible outcomes, okay, and each one of them equally likely. So the probability will be 4 over 10. Number 25. What is the probability of getting E? That is an even number less than 9. Even number less than 9 are 2, 4, 6, 8. And those are translated into, the probability is, that will be 4 out of 10. Number 26. What is the probability of getting an odd number? How many odd numbers there? 1, 3, 5, 7, 9.
5.
That will be 5 over 10. So simple enough, right? When the events are equally likely, that's actually quite easy to do. Yeah, that's actually quite easy to do. When it is equal likely, just see how many possible outcomes, and the probability for each outcome will be 1 over whatever that is. Number 28. In a survey of 1,100 female adults, usually we use this notation, N of the sample space. Okay, the number of elements in the sample space is 1,100. Okay, it was determined that 341 volunteered at least once last year. So the number of people who volunteer is 341. Okay, now what is the probability that a randomly selected adult female volunteered at least once in the past year? So you see, what we will do here is basically the relative frequency. Okay, the proportion of female adult who volunteer. So the proportion or the probability of volunteered, a female volunteer in the past will be 341 over 1,100. Okay, I think that will be 0.31. Okay, interpret this probability. Well, if you do it 100 times, for example, then you expect around 31 of them volunteer in the past, at least once in the past. Okay, maybe more than 31, maybe less than 31, but it will not be far from 31. Okay, is it possible that it is far from 31? It's still possible though, but the probability is so small. Okay, the probability is so small. Number 32, this gets more interesting here. Exclude leap years from the following calculation and assume each birthday is equally likely. You know this is not true. Okay, birthday actually not equally likely. Believe it or not, we have more people born pretty much at the beginning of September. That's one, for example. Okay, that's one, for example. And for some strange reason, I did some computation before. Okay, if your parents born a birthday, for example, in April, then your birthday is more likely happen in either December or January. If your parents' birthday is in August, then there's a chance your birthday actually happens in March or April. Now you ask me, you think about yourself why that happens. Okay. But using the assumption of equally likely, then determine the probability that a randomly selected person has the birthday on the first day of a month. So probability of birthday on first, January the 1st, February the 1st, March the 1st, and so on and so forth. Now, how many firsts in a year?
12.
There are 12 out of how many days? Yeah, we exclude leap years, right? So regular year, 365. Okay, now then part B. Determine the probability that a randomly selected person has a birthday on the 31st of a month. On the 31st, that's actually a good question. How many 31st in a year? This one is good. This one is good. January, March, May, and then July.
September?
Huh? September actually don't have 31st. July and August. And then October. And then December. Right? 1, 3, 5, 7, and then 8, 10, 12. So they are 7 31st in a year out of 365.
I've never had to think about that. So I can put
No,
that
no,
in everything.
no. Trust me, you will never need to think about this for the rest of your life. But we use this as an example on how to think for other case. So don't think of this like, oh, this is a case that I will never see anyway for the rest of my life. So why I need to learn it? No, this is just a reflection on how we think instead of like what's the answer. Okay, so instead of what's the answer, it's about how we think. Okay, so imagine if you have an apartment, right? A big apartment, or maybe a dorm, okay, and then you have an elevator, okay, like 3 stories dorm. Okay, in the first floor there are 10 rooms. Second floors there are 12 rooms, and then the third floor there are, let's say, uh, 8 rooms. Okay, and each room only have one person. Now, what is the probability the elevator will go to the third floor? Don't you think it's actually just the same idea, right? Okay, and that's actually a good question. What is the probability that when somebody from the first floor, what is the probability it will go to the third floor? If somebody on the first floor use the elevator, what is the probability it will go to the third floor? Any idea? The way we think for this question is actually the same to the way we think for that number 32. If somebody used the elevator in the first floor, the probability it goes to the third floor will be 8 out of 20. Not 8 out of 30, no, not 8 out of 30. Because if that person needs to go to the first floor, that person will not use elevator, right? So if that person use elevator, then it must be either that person on the second floor or the third floor. Okay, now the other question is, I can switch the question in totally different way. Okay, now if somebody walk through the door of this dorm, what is the probability that person will go to the third floor? Now the thing is, when that person goes through the door, means that person may be part of the first floor, right? Either the one here or the one here or the one here. So what is the probability that person will go to the third floor? It will be 8 out of 30. Because we don't know yet if this person will go use the elevator or not. But once we know this person used the elevator, then it won't be the first floor. Okay, suddenly the probability to go to the third floor becomes 8 out of 20. Okay, now you see that how we combine critical thinking and computation, right? Critical thinking and computation. Now going back here, part 3, part C, determine the probability that a randomly selected person was born in December. How many days in December? There are 31 days in December. Now, Thomas, how do I know that December has 31 days? I'm sorry, I cannot help you with that one. Okay, for you to survive this class, you need to have some basic general knowledge. Okay, that's honestly, that's something I don't know how to answer though. How do we know, Thomas? I don't remember that December has 31 days. Then I just like don't know how can you survive how many years living and end up taking my class without knowing that fact. Part D, determine the probability that a randomly selected person has a birthday on November 8th. Exactly on that one particular day, November 8th. That's only 1 out of 365 days. Now, if you just met somebody and she asked you to guess her birthday, are you likely to be correct? The probability for that we guess that person's birthday randomly and correct is probability to be random and correct. Will be 1 over 365. Now, are you likely to be correct? The question of likely to be correct in our probability class is set at 5%. Okay, 5%. Now, less than 5% probability means it's unusual. So when we compute this 1 over 365, that's 0.003 something or 0.002. Okay, you can use your calculator, but you know that this is less than 5%. Therefore, the probability I can guess somebody's birthday correctly in one guess is unusual. Therefore, it is unlikely. Okay, the way we define unlikely is not more than or less than 50%. No, in statistics, unlikeliness, unusualness is defined to be less than 5%. Okay, now part F, do you think it is appropriate to use the methods of classical probability, equally likely, to compute the probability that a person is born in December? Now we know that's not true. Okay, no. So this method of computing probability of somebody's birthday in part C, for example, this method is not a good method. Okay, because we base on a big assumption that you have 365 days to be born, but that decision is actually more or less made by your parents. Okay, and of course, I don't expect them to do something unusual on weekdays, for example. I just make up. Just think about it. Okay, be creative in your thinking. Okay, it must be some special day that they see the urge of doing such thing. Okay. Number 36. We go a bit further. In a national survey conducted by the Center for Disease Control to determine college students' health risk behavior, these college students were asked, how often do you wear a seat belt when driving a car? Now, this is the frequency. Now, we call this frequency distribution. Now, part A, the question is, construct a probability model. Our textbook keep on using the phrase probability model, okay? But the correct terminology is supposed to be probability distribution. Okay, the correct terminology is actually probability distribution. I don't even want to say that that's one way to say it, just another. No, it's you can read other textbook, and out of 100 textbook, maybe only 2 say it is probability model, and those 2 are written by this same author. Okay, now then how do we construct probability distribution? Now we already have the frequency. Then the probability, basically we can extend that table and construct the relative frequency. Okay, construct the relative frequency. But let's find out first what is the total. Let's find out first what's the total for how many people being surveyed. So I will add all these numbers, 118 plus 249 plus 345 plus 716 plus 3093. I get 4521. So the probability will be equal to the relative frequency. This is 118 over 4521. That gives me 0.02610, 5 decimal places. Okay, now let me do it on the right hand side here so that we can see it better. Okay, so the response, and then relative frequency. Which will be our probability. The response never is 118 over 4521 in decimal. If you make it decimal in my class, 5 decimal places. Rarely. That's 249 over 4521. I get 0.05508. Sometimes that's 345 over 4521. I get 0.07631. And most of the time, that's 716 over 4521.
0.15837.
0.15837. Don't forget the leading zero, okay? Please don't forget the leading zero. And always, which is a good one, always wear your seatbelt. Always wear your seatbelt. Not only because if you don't wear your seatbelt, that's against the law. No, no. Even if it is up to your personal liberty, personal freedom, wearing a seatbelt is never wrong. Thomas, I have seen people die because of seatbelt. Okay, compared to how many people die because they don't wear seatbelt. We learn probability and statistic, right? This is actually the best way and the best time for us to have that kind of argument academically, okay? So when people ask me, Thomas, what will you say to somebody who don't wear seatbelt? Well, that person's just stupid. Okay, but Thomas, don't you think that's offensive? No, you asked for my opinion. I tell you my opinion. What's so offensive about that? Okay, but why you call that person stupid? Because what are you about to lose if you wear your seatbelt, huh? Right? If no accident and you wear your seatbelt, then nothing wrong, right? But what happens if you don't wear your seatbelt and you have accident? Okay, but nothing will happen to me. Hold on, not yet. Because when you have an accident and the insurance company found out that you don't wear a seatbelt, okay, and your insurance premium will increase. Okay, at least think from that point of view. Okay, at least think from that point of view. Not to say that in reality that seatbelt does, I think I should say seatbelts do reduce the severeness of the injury you get. Okay, so please wear your seatbelt. Well, okay, this is still my opinion. If you disagree with me, fine, you know, but when it comes to like I give you a ride and you insist not to use seatbelt, then I will drop you off right on that spot, even if that's on the freeway. If like I give you a ride and then on the freeway suddenly you take off your seatbelt, then I will drop you off there right away. Okay. Why? Because I'm the one driving. You have the right not to wear your seatbelt. I have the right to choose my passenger. Okay, but suddenly some people talk about, well, you know what? Don't you think that's not nice, Thomas? Well, it's first of all, I give you a ride and you don't listen to me when I'm the one driving. That's so not right. Don't talk about nice. That's not even right. Okay, well, anyway, don't forget every time you have a probability distribution, at the end, at the bottom, you need to add the probability, and it's supposed to be 1. Okay, it's supposed to be 1. Part B, is it unusual for a college student to never wear a seatbelt while driving a car? And how do we know it's usual or unusual? Look at the probability. Probability of never wear a seatbelt is 0.02610, which is less than 5%, right? So that event is unusual. Okay. So when I say you're a strange person, if you don't wear a seatbelt while you drive the car, okay, that's strange. Oh, by the way, that gives me something. Long time ago, I think the first year I came to the United States or the second year I came to the United States, one of my best friends, so I have a best friend, happens to be a girl. Now, her boyfriend gave me a ride. A good thing it's nearby my home. It's like only 2 blocks from my home. And then he said, oh, let me give you a ride home. Okay. But then when he gave me a ride, he didn't want to wear a seatbelt. I said, well, why don't you want to wear a seatbelt? He said, well, I just don't get used to it. That's what he said. And then I said, why don't you drop me off here right away? I just like, no, I don't want to be in your car. I said, why, Thomas? You're so strange. I said, well, you're the one strange. people, it's first of all, that's your car. So one way to protect your insurance is to wear your seatbelt, dude. He didn't want to, so I asked him, like, he just drop me off here. Okay, so I walk home in the rain. And he never give me a ride anymore. And couple of months later, I heard that he had an accident, a really bad one. Really bad in this sense, really bad in this sense. His car's okay. His car's okay, but he himself badly injured because he was thrown to his windshield, and that's a BMW. That's bad, huh? Okay, not that I'm happy to tell you that. I mean, of course, when I heard that is he okay, then I think he stayed in the emergency room for like 2 days. You know, which can easily be avoided if he had worn his seatbelt. Okay. Now the sad thing is this: he was actually get hit. That somebody hit him. Okay. But then when they found out he didn't wear his seatbelt, he was at fault right away. He was at fault right away. It's like the police didn't even want to care about anything else. It's like you purposely go against the law. Okay. Now, of course, when it comes to witness, some people say that it's his fault. Some people say that the other person's fault. It's about the red light, right? Who went through the red light. But you can have different witnesses saying different things on during that time. And yeah, he just lost it right away once they found out that he didn't wear his seatbelt. So he needed to cover his own emergency room costs. No, not a good idea. Okay, you can have a BMW without the brain of a BMW brain. That's not good. That's a waste of money. Okay, number 38. The following data represent the number of live multiple delivery births, that's 3 or more babies, for 2012 in 2012 for women from 15 to 54 years old. Okay, and I would like you to construct the probability distribution here. Okay, so part A, I would like you to construct a probability distribution. I believe the procedure we did in the previous question is clear, right? So the age from 15 to 19, 20 to 24, 25 to 29, 30 to 34, 35 to 39, 40 to 44, 45 to 54, and you have the probability here. Do you think you can do it on your own? Very similar to what we did right above this question. Okay, and then let me ask you to answer part A and B. Instead of doing A, let me ask you to do B and C right away. But I need you to give me the argument. Okay, I need you to give me the argument. Let me give you maybe 3 minutes to do this. Just do B and C. Just do B and C. Okay, for 15 to 19, to know if it is usual or unusual, I need to get the relative frequency. That will be 44 over what? Anybody can tell me? What's the total?
The 2.
Huh? No, the total if you add all these numbers.
4,919.
4,919. Can anybody else confirm that? That's right. Okay, good. Thank you. So the relative frequency for multiple birth for women 15 to 19 is 44 over 4,919, which is 0.00896. Now, so is it unusual? You will say usual or unusual. And how do we know?
Unusual, less than 5.
Unusual because less than what?
5%.
Less than 5%. Okay, likewise for 40 to 44, that will be 332 over 4,919. That will be 0.06749. Oh, that's more than 5%, huh? So that's not unusual. Okay, because at least 5%. The probability
Professor, I think I overthought the problem. I was thinking of it in an interval where I had to plus 15 plus 19 divided by 2.
plus 15 plus 9. Oh, no, that's if you try to find the midpoint of that age. Yeah, that's if you try to find the midpoint of that age. Yeah, or at least probability. Is at least 0.05. Okay, now right now it's 5 o'clock. I would like to take 10 minutes break before we go to 5.2. Now in 5.2, later on, I will first do problems. I still need to make sure that you know the concepts and the notation from Venn diagram. Our textbook doesn't really do Venn diagram, that's the thing. Right now it's 5:03. Let's come back at 5:15. Now, in this 5.2, we will learn about union, intersection, and complement. Okay, notation, which I believe I already mentioned in my lecture. Okay, let A and B are events, or you can also say sets. Then A union B is the set of all elements or events in A or B or both. So once it is in either one of them, you count it in. Okay, while A intersection B, so it's a capital U without the tail, that's the union. Now, the upside down of that is the intersection. Not this, not this, not this. This is not intersection. This is a big size lowercase n. No, not that one, not that one. Okay, and the union also not big U, even though that's actually where the word coming from. Okay, the notation coming from, but it's a U without a tail. Now, A intersection B is the set of all elements in A and B simultaneously. In both, I think I should say in both A and B. A and B. So it must be in both of them. Okay, so pictorially, suppose we have a Venn diagram, and let's say this is set A, this is set B. This is set A, set B. Now, D intersection refers to this part here. Okay. Those that is in circle A and also in B. Okay, so the ones in the blue region is what we call A intersection B, the one they have in common. On the other hand, when we say the union of two sets, so let's say this is set A and this is set B, then the union refers to the region either in A or in B, which includes both. So once you satisfy one of the requirements, then I count you in. Okay, so the one in yellow here is the region where A union B. Okay. Once it is in either one of A or B, you count it in. Okay, now as you can see from here, let me give myself more space. Notice that A intersection B must be part of A. Okay, this is A, right? This is the set A. Now notice that the intersection must be part of that circle. Okay. And in fact, it is also part of B. In other words, A intersection B is also part of B. It's a subset B also. Now, consequently, then Consequently, you will see the probability of D intersection A and D will be less than equals to the probability of A. Probability of A intersection B, therefore, will be less than equals to probability of B. Okay, it's actually more difficult to satisfy both requirements instead of only one requirement. Okay, on the other hand, we see that A union B is always greater than A, right? This is A here, this is A. Okay. Now you see the yellow one is larger than the green one, right? The total yellow, including A, is greater than A itself. Okay. Likewise, set B is always subset of A union B. Now, consequently, the probability of A must be less than equals to probability of the union. Probability of B must be less than equals to probability of the union as well. Okay, now then last one, the complement. The complement of A we denote it by, our textbook use this notation, A and then superscript C. However, that notation is actually harder to use. So in my class, I will use A bar. In fact, that's actually a more common notation when it comes to complement. Okay, some other textbook, they use A prime. Okay, I will use this one. I will use this one. Okay, now the complement of A, which is A bar, is the set of all elements in the universe, the sample space, let's say, but outside of A, but not in A. So pictorially, if we have a Venn diagram with set A somewhere there, okay, let's say this is set A here, then the complement refers to everything in the rectangle in the Venn diagram, but outside of that, outside of A. So the green one here, the one outside of A. Okay, so the green one will be outside of A complement. Now you will see that probability of A plus probability of A complement, the complement of A, must be equal to 1. It's either you are in A or outside of A. Okay, cannot be neither, cannot be both. Okay. Therefore, we get a formula when we need to compute the complement of A, one way to do that is to subtract the probability of A from 1. Okay, now I really want to start working on this, but I guess I will need to postpone it a little bit later, maybe at the third hour, then we will start working on that. Okay, but I need to make sure that we understand the notation being used. Okay, now first one, consider the following Venn diagram. Example 1, consider the following Venn diagram. A Venn diagram is a rectangle, okay, that represent the universe, and in there you have sets. Let's say this is set A, and this is set B. Okay, now if you see I use this notation, a dot with 1, a dot with 2, a dot with 3, a dot with 4, 5, 6, 7, 8, for example. This means A has the following element: 1, 2, 3. Okay, why? Because set A covers this part, this circle, right? Okay, so including 3. There are 3 elements in set A, and those elements are 1 and 2 and 3. How about the elements of set B?
3, 4, 5, 6.
3, 4, 5, 6. That's right. Now then, how about the element in the intersection?
3.
Just 3. That's right. How about elements in the union?
1 through 8.
Are you sure?
No.
1 through 6. Right? You see? It's 1
So
through
anything
6.
external is not included in the union?
That's why you call that external.
Ah, okay.
Right? Okay.
Yeah.
So how about the complement of A? Which elements are not in A?
There's 7, 8.
And besides 7 and 8?
4, 5, 6.
4, 5, 6, also outside of A. 4, 5, 6, 7, 8. Okay, how about the complement of B?
4, 5, 6?
What? Are you sure? No, you see 4, 5, 6 is actually inside
1,
B.
2, 3.
Are you sure including 3?
3?
No, I just want to say 1, 2.
1, 2, and then what else?
8, 7.
8, 7. Is it okay? So far, so good. Now let's make it a bit harder. Okay, let's make it a bit harder. How about the complement of A union B? This one is hard. This notation means outside of the union. Outside of A union B. What will that be?
7, 8.
7 and 8. That's right, 7 and 8. How about the complement of D intersection?
Is it none? Or 7, 8?
It's everything except 3.
Everything except 3. That's right. Okay, because the intersection is only 3, right? The
Right.
intersection is only 3, so the complement of everything, the complement of that 3 is 1, 2, 4, 5, 6, 7, 8. Okay. How about this one here? This is a bit harder. This is a bit harder. Complement of A union, maybe not union first, intersection. Complement of A intersection B.
3 to 6.
No.
No.
So this is basically outside of A, outside of A,
4 to 6.
and also at the same time inside B.
4, 5, 6.
4, 5, 6. That's right. That's the set of 4, 5, 6. Now, can you try? How about, you know what? I want to do it below, but I'm afraid that okay, you know what? I do it this way. So how about A intersection, not B? You try this. What is the interpretation first?
Everything in A
Everything in A,
outside of B.
outside of B. That's right. And everything in A, but at the same time outside of B. And what elements will those be?
1, 2, 8, 7.
1, 2, 8, 7? I think only 1 and 2. 8 and 7 are outside of B, but they are not in A. Right? It has to be inside of A and then also outside of B. Okay, so when it comes to intersection, it has to satisfy both. It has to satisfy both conditions. What are those conditions? It has to be inside of A and then outside of B at the same time. Okay, now next, how about not A union B? This is outside of A or inside B.
4, 5, 6.
Inside B is 4, 5, 6. Okay, but there is more. Let's start with outside of A. What are outside of A?
7,
What are outside of A? 4, 5, 6, 7, 8. Those are outside of A, right? Now then, how about the ones inside B? 3, 4, 5, 6. But 4, 5, 6 already registered, so I just put more 3 in. Okay, so I hope you can contrast the difference between intersection and union. Intersection, it has to satisfy both. It has to be outside of A and at the same time inside of B.
Okay, I was lost for a minute how 3 was. I thought we wasn't counting 3 because it was kind of inside of A too, but we're not thinking of it that way. We're looking at
Well,
it.
3 is in this union. 3 is in this union because it is inside B.
I understand. It's the U that makes the difference.
Yes, the U. So as long as you satisfy either one of them, it's union, right? So basically you put it together. As long as you satisfy one of them, then we count you in.
No, I was almost fine.
Intersection, if you only count it if it satisfies both. Okay. If union, it just need to satisfy at least one of them. Okay, let's try one more. Let's try one more. How about
What do you mean by bit? What's
A union complement of B? Okay, I'll give you 1 minute to think about this. Okay, what will that be? This is in A or outside B, right? In A or outside B. And then that will be
1 and 2.
1, 2 are in A.
8, 7.
Definitely.
8, 7.
Finish A first. We are not done yet with A. What are in A? 1, 2, and 3 also, right? 1, 2, 3 in A. Now then, how about the one outside of B? Outside of B's are 1, 2, which we already registered 7, 8.
Oh, I'm so confused.
Okay, it's about this. If you get confused, you are normal. Don't feel bad. Okay, I know that's this is the one requires a lot of critical thinking. When you do comparison between these two, okay, the difference is with the word and, which means it has to satisfy both, compared to the word or, which means it has to satisfy either one. Okay. Imagine this. Suppose I say to my mom, and this is actually, I think in my lecture I said this before, I will marry somebody if that person is cute and rich. Compare that if I said I will marry somebody if that person is cute or rich. Under which situation I will more likely get married?
Cute or rich?
Cute or rich,
Cute or rich, why?
because it's either or. The other
Yeah.
one is all or none.
That's right. So all I need to have here is if that person satisfy either one of them, right? Either one of them. While the one here, it has to satisfy both of them. So use your instinct a little bit. When we say or, means it just need to satisfy either one of them. It's either in A or outside B. So as long as it satisfies in A, you count it in. As long as it is outside of B, you count it in. That's for or. Now, for N, on the other hand, the one right next to it, for N, compare. Inside of A and at the same time outside of B. So first it has to be inside of A. So that's 1, 2, 3. But it also have to be outside of B. The one outside of B are these. Right? So only 1 and 2 are in A and outside of B at the same time. Do you start to see the difference? Intersection means it has to satisfy both. Union means it just needs to satisfy either one of them. Okay, now I will get further in. The way I draw the Venn diagram above is to tell what are the elements in A, in B, outside of A, outside of B. Okay, what are the elements? Now, contrast that with the following way of writing, describing Venn diagram. Suppose I have a Venn diagram Okay, and then I have set A, and this is set B. A and B. I say 2, 1, 3, 2. Notice that I don't use that dot. Notice that I don't use that dot. No, I don't use those dots. Now, if you see a Venn diagram like this, it implies that those numbers are the number of element and not the element itself. Okay, if there's no dot, right? So the number of element in A is equal to 3. There are 3 elements in A, 2 of them outside of B, 1 of them inside B. So a total of 3 elements inside A. Okay?
Professor, how did you get 3 and you highlighted 2?
2 and 1.
Adding together?
Yes. Notice that I don't use the dot. I don't use dot. If I use dot, means 2 is an element and 1 is an element, right? No, I don't use dot. If I don't use dot, it means it reflects the number of elements. Okay, there are 2 elements outside of B and 1 element inside of B. The number of element in A will be this. That's the number of element. 2 of them outside of B, 1 of them inside of A. I'm sorry, inside of B. Let's do more. How many elements in B?
Four.
4. That's 3 plus 1. Right? Maybe I use this one here. That's 2 plus 1. How about the number of elements in the intersection?
Seven.
No. Intersection.
Oh, so it's 2 plus 1 plus 3, right?
That's not intersection.
1?
Just 1.
Oh,
The
okay.
one, yeah, the one you referred earlier is the number of elements in the union.
Okay.
There are 2 plus 1 plus 3 elements in the union. Okay, the elements, the number of elements, a total of 6 in the union. How about the number of elements outside of A?
5?
Outside of A are 5, and those are 3 plus 2, right? How about the number of elements outside of B?
4?
Outside of B will be 4, coming from 2 plus 2. Yeah, these 2 plus these 2 outside of B, right? So there are 4 elements outside of B. That's right. Okay. Now, before I go on with a more complicated examples, I want to emphasize the difference. Notice that this example 2 here is the summary of example 1. But Thomas, I saw numbers and I also saw numbers. Now, the difference is if I don't use dot, the one here use dot, right? Means number 1 is element of A. Number 2 is element of A. Number 3 is also element of A. Okay. Now, B consists of 3, 4, 5, 6. Here you see 1. It doesn't mean that 1 is element of B. No, it just say that the intersection has 1 element, but doesn't mean the element is 1.
Would you say that the decimal is similar to connecting dots, and then without the decimal, it's more adding the dots? Adding the numbers, sorry, not the dots.
No. the dot represent the elements. So there are elements. So I can put it this way.
Action.
Maybe I can put it this way. So A, for example, I use a star. And this is a R. This is a B. This is, no, don't use B. Let's say this is K. And this is H. This is H. This is G. This is P. And this is Q, let's say. Okay, so how many elements in A in this picture?
It's the star, R, and K.
Star, R, and K. How many elements?
3.
3 elements. That's right. There are 3 elements, and those elements are star, R, and K. Okay, so I can change the notation becomes like that, and the summary still look like this. This is the summary. Notice that I don't use dot here, right? If I don't use dot, then those numbers represent the number of elements instead of the actual element. Okay, now I need to reverse those back though. I need to reverse this back. Otherwise, I get confused. Now, how about the number of elements in A but not in B?
Four.
Ah, are you sure? I don't think so. Which region is in A but outside of B? Inside of A but outside of B only refers to this crescent here.
2.
There are 2 of them. How about the number of elements not in A and outside of B? Okay. Not in A, but inside of B.
5. No, 6.
Outside of A and at the same time inside of B. This is the region outside of A, but inside of B.
3.
There are 3 of them. How about the number of elements in A or outside of B? Ah, this one is more difficult. Let's identify first what are the elements in A or outside of B. The one inside of A are these. These are the one inside of A, right? Now, the one outside of B are these. Those are the one outside of B. Now, the thing is, if it is union, then once you color it, you count it. For intersection, it needs to have 2 colors. So you see the intersection here. This is the intersection. You color it twice, right? The intersection is 2. Okay, there are 2 of them. Now, how about the union? The union is, as long as you color it at least once, you count it in. 2 plus 1 plus 2. There are 5. This is the first 2. This is the 1. So there are 3 elements in A. Okay. Or outside B. The one outside B are these 2 which we already count and these 2 which we didn't count yet. That's how we get that 5. You try this. Number of elements in outside of A or inside of B? How many elements outside of A or inside of B?
2 plus 3 plus 1.
Which two you're talking about?
The outer two.
The outer two, okay, this one here, and then plus
Yeah,
3. So these two and 3 are 5 elements outside of A, right? Okay, so that's right so far. And then union B, the one inside of B, are 1 element and these 3 elements which we already counted. So the number of elements outside of A or inside of B will be that 2 plus 3, which is outside of A, plus 1, which is inside of B. Now, if you find it to be difficult here, again, I say that, especially the last 4 questions, if you find it to be difficult, you are actually normal, because that's what I encountered so far. Every time I mix union intersection with complement, you start get shaken. It's like, what the heck is that? You know. So if you have hard time, you are normal. That's what I also found usually. In fact, I also see that students who don't find it to be difficult, very likely, because you don't pay attention. So you don't even see the issue. Okay. Now, I'm not trying to say that if you get it already, it means something wrong with you. No. It means you are excellent. Okay, you are excellent. But I don't really see people look at this and know it right away. What I usually see are people who don't get it right away, and that's how you know that you need to learn more. Or people who was like ignorant, they don't really pay attention, so that they don't even know that they don't know. Okay. Now let's try the last 2 problems. Okay, the last 2 problems before we go to probability. Number of element not in A and not in B. That one is difficult. Number of element not in A, union not in B. Number of element not in the intersection. Number of element not in the union. Okay, think about these 4 questions. Maybe you do these 4 questions, think about that, and then we take a little break. We come back at 6:10 maybe. Come back at 6:10. Okay. Then after that, we will do probability. Okay, after that, we will do probability. Right now, we just see what this notation mean, what that notation mean. So how many elements not in A and at the same time not in B? Not in A refers to this guy and this guy. That's not in A. Not in B refers to this guy and this guy. Okay. Now, because it is an intersection, it means it has to satisfy both. It means you need to have colored twice. So the number of elements not in A and also not in B is only 2. Now, on the other hand, the number of elements not in A or not in B means they just need to be colored once. Okay, just need to be colored once, at least once. So the number of elements not in A, that's 2 and 2. Or not in B, that's 3 and 2, but only 3 not registered yet. So there are 7 elements not in A or not in B. Now, second from the last, number of elements not in the intersection. Now, notice that the intersection is this guy, right? That's the intersection. Everything outside of that guy. How many elements? Number of elements outside of the intersection, that those are 2 and 2 and 3. That will be 7. The number of elements not in the union, this is the union. Okay, now the one outside of that, only this guy. Okay, now you will see, I believe that's not in our textbook, but it's worth mentioning, something called the Morgan's law. The Morgan says that the complement of the intersection is the same to the union of the complement of A, complement of B. So you see the union, number of union, the number of elements in the union of the complements equals to the number of elements in the complement of intersection. These two are the same number. Okay, and the number of elements in, the complement of the union of A and B is the intersection of the complements of A and complement of B. That's why you see these two numbers are the same. Okay, worth noticing. You don't need to memorize this though. This the Morgan's law is just a side note. You can call this as just a side note. That's just a side note worth mentioning, and even give credit to that guy named the Morgans. Just side note. We will never explicitly use that. Now, what I want to do next is go into the probability based on the numbers we did earlier. So I will quote this Venn diagram again. I will quote this Venn diagram again. Call that example 2B. Okay, now this is what we will do. Select one element from the group or from Venn diagram. Okay, and then let's say part A. Find the probability of getting an element from A. Find the probability of getting an element from A. Now, the probability of getting an element from A is equal to the proportion of A compared to the whole Venn diagram. Now, how many elements in the Venn diagram?
4?
No. Not 4, not 4. How many elements in the Venn diagram? There are 2
7.
plus 1 plus 3 plus 2. There are 8 elements in the Venn diagram. Okay, how many of them in A? There are 3 in A. Notice that I don't use a dot here. I don't use a dot. If I use dots, right? If I use dots here, then there are 4 elements in the Venn diagram. But no, I don't use dots. Means those numbers represent the number of elements in that region. Okay, now the number of elements in A cover this. Okay, that's the number of elements in A. Therefore, if I need to select one element at random, what is the probability that one element will be from A. That will be 3 over 8. Maybe I write how I get that 3. That's 2 plus 1 over 8. That's 3 out of 8. The number of elements in that set divided by the total element in that Venn diagram. Let's see part B. What is the probability of selecting one element from B? Then how many elements in B?
Can you repeat that? I'm sorry.
How many elements in B?
4.
That's 1 plus 3, 4. Out of how many elements in the whole Venn diagram?
8.
8. So the probability of getting something from B is 4 over 8. How about if I want to compute the intersection to find the probability that we get someone in A and B at the same time?
Five over 8.
No. How many elements in the intersection?
1.
Only one. There's only one element in the intersection, so your probability will be 1 out of 8 possible outcomes. Okay, how about part D, probability of having the union of A and B, getting something, an element from A or B. And how many elements in the union?
6 over 8.
That will be 6 out of 8, and we get that 6 from 2 plus 1 plus 3, right? So that's 6 over 8. Actually, if you can reduce, you need to reduce, or if you want, you can change it to decimal. How about the probability of getting something outside of A?
5 over 8.
Outside of A will be 5 out of 8, that's right. And how do you get that 5?
3 plus 2.
3 plus 2, the ones outside of A. Okay, the probability is 5 over 8. How about the probability of getting something in A but not in B?
2 plus 2.
No. In A but not in B. Only one element. But how many elements in A and not in B?
2.
2. Okay, there are 2 out of 8. These 2 here, this guy here. Okay, these are the number of elements in A only. Okay, please distinguish when I say the number of elements in A. There are 3 elements in A, but there are only 2 elements in A only. Okay, you see. I hope you see the difference. Okay, the number of elements in A is there are 3. The number of elements in A but not in B, only 2. How about part G? Find the probability of getting an element not in A or in B.
2.
In A, not in A or in B. How many elements not in A? This is an or, not an and. Outside of A refers to this.
1 plus 2.
There are 5 of them, right? Okay, that's outside of A. Or inside of B. Inside of B refers to this. Because this is union, then as long as you color it at least once, you count it in. That will be 2 plus 3 plus 1. That will be 6 over 8. That's 3, 4. Now, I think here's the thing though. Let me go back to my lesson earlier. I did say that I want you to learn, watch lesson 6 and 7. Okay, but there's a chance that on Monday we only cover up to lesson 6. But watch both of them anyway, just in case we can spill over to lesson 7. Okay, now, because here's the thing, I have one examples that I don't think I will cover today. It will be too heavy for you, too much hard thinking. But it will be something look like this. It will be something look like this. I will do it later on, not today, but I just show you what happened if I have A and then B and then C, you know, like 3 circles. And then, for example, how do you express this region here? That's the region of inside A and C and outside of B. Now, that's what we learn on Monday. Okay, today, not yet. It could be too heavy. It could be too heavy for you. I prefer you to, during this weekend, when you study, review my discussion on this example 2 and example 2B. Okay, now example 1 and 2 actually related though. Okay, 1 and 2, you really see what are the elements. Example 2 tells us the number of elements. Now, example 3, how we relate number of elements with the probability for an event to happen. Okay, now let's go back to, let's do some nice stuff first, something interesting. One of the things I wish you can do after you take my class is ability to count cards. Okay, at least a simple one, right? Okay, now I hope after you know a little bit about counting cards, then you also know don't go gamble. Okay, the odds actually against you. Okay, the odds actually against you. Now, this is what we call a deck of cards. In our statistic class, when we say a deck of cards, it refers to these 52 cards. Okay, it refers to these 52 cards and not including jokers, only these 52 cards. There are 4 suits in these 52 cards. The first one is club, or sometimes they call that, I'm sorry, spade. This is spade. Then we have heart. We have club. Sometimes they call that clover. And diamond. There are 4 suits. Now, each suit consists of 13 cards. From ace, which also counted as 1, sometimes at 11 when you play blackjack, okay, and jack, queen, king. Now, each suit has these 13 cards. Okay, each suit has these 13 cards from ace to 10, and then jack, queen, king. A card is called a face card if it's either jack or queen or king. So these are the face cards. Basically, instead of numbers, it's a face, like a jack or queen or king. Okay, those are face cards. There are a total of 52 cards in a deck. Now, let's think about, let's play with this a bit. Okay, bring this up, okay, and then from a deck of cards, and in my class, just like other probability statistic class, when they say a deck of cards, it refers to 52 cards. Again, not 54 including jokers, no. It refers to 52 cards. Unless they specifically say including jokers, then you know that's 54 cards. Okay, now from a deck of cards, which is 52 cards, select one card at random. Now you see, because these cards here, these 52 cards are all identical except on the one side, right? Okay, if you select one card at random, then it will be equally likely. Okay, the question is find the probability of getting, let's see, let's do it in words and then I teach you how to use notation. Find the probability of getting a hard card. Notation. Probability of getting a hard card is probability of hard. Then you ask yourself, how many hard cards available? How many hard cards available in this deck? There are 13 hard cards out of 52 cards, which when you reduce, you will see this is 1/4. Are you with me? The number of hard cards divided by how many outcomes you have in total. Okay, now how about what is the probability of getting a red card? Probability of getting a red card, the notation P, capital P, parenthesis the event, red, or you can also say red card. How many red cards here?
26.
26, that's right, the number of heart and diamond cards, right? Which when we reduce, you will see that's equals to 1/2. Next, how about the probability to get an ace?
Four over 52.
Notation, probability of ace, and there are 4 ace cards out of 52. Reduce, that becomes 1/13. That's good. Okay, furthermore, how about the probability of getting a hard ace?
One over 52.
1/52, so you can count it well. Okay, how about the notation?
P. Ace.
Hard
Heart. Ace.
intersection ace. It has to be hard and ace at the same time. Okay, when we say a hard ace, that's a hard and ace at the same time, right? Now, as opposed to a hard or an ace.
Probability heart union ace.
That's right, probability hard union ace. Now let's see how many hard or ace. How many hard or ace? I need to make it smaller now. How many hard or ace? These are the hearts, right? There are 13 hard cards, right? Okay, and then how many ace cards?
3. 4. 4.
There are 4, but 1 already counted. So you are actually right. You add 3 more. Okay, so you will see that the way we count this is that you only count it once, right? So there are 13 hard cards. There are 13 hard cards plus 4 ace card, but you need to subtract the double count. Okay, this guy is counted twice, right? Okay, so how many ace union heart, the probability of getting ace or heart will be just 16. But technically we will, let me just write it this way. There are 13 heart cards plus 14 ace card minus one guy double counted. Does it make sense? Okay, so that's 16 over 52. If I reduce by 4, that's 4 out of 13. Pictorially, if we try to describe that in Venn diagram, okay, so I'm not trying to confuse you. I'm trying to show you that what we did in Venn diagram earlier is actually in line to what we do here. So we have 13 heart cards and 4 ace cards, right? Now, one of them in the intersection. There are 12 heart cards, which is not ace, and there are 3 ace cards, which is not heart. Does it make sense?
Yes.
Right? Okay. So if you think about it, then how many heart or ace? Well, there are only 16. Right? Yeah. 13 of them heart, 4 of them ace, but 1 of them double count. Okay. 1 of them double agent. Okay. 1 of them double agent. So double it, one of them double counted. Okay, let's do more. Let's do more. This time you do it. This time you do it. How about the probability of getting a diamond or a heart? Then you count how many elements in how many cards are diamond. Union that with number of cards, heart card. So how many cards? Diamond or heart? 13 for each, right? There are 13 for each, and there's no double count. There's no double agent. The notation will be probability of diamond or union heart. That's equals to 13 plus 13 over 52. Eventually, you will see this is 1/2. Now, the last one, it's either very easy for you or very hard for you. What is the probability of getting a diamond and a heart?
Probability union heart.
Diamond intersection, it's an N, right? Heart. How many cards, which is a diamond and heart at the same time? How many cards are diamond and heart at the same time?
0.
0. That's right. Okay, so the probability of getting a diamond and heart at the same time, only one card will be 0 out of 52. That is impossible. There's no way. In fact, if you think about it, we say that the intersection of diamond and heart is actually empty set. There is no intersection. Okay, these two sets are disjoint. Okay, therefore the probability for the intersection to happen is 0. Okay, now if the intersection of two sets is empty set, then we say diamond and heart are disjoint. Now, in probability statistics, we also call that, also known as mutually exclusive. Which simply means they cannot happen at the same time. Okay, they cannot happen at the same time. Just like traffic light, red light and green light are disjoint events. They cannot happen at the same time. I mean, one way to know that your traffic light is broken, that it happens at the same time. You see green light and red light on at the same time.
Like,
right?
You can't be married and divorced at the same time.
They cannot even get married, basically. They cannot happen at the same time. Okay, that's what we mean by mutually exclusive. Like the sun cannot rise at the north and south at the same time. Thomas cannot be at home and at West LA College at the same time. You know, those are two disjoint events. Okay, I can work at West LA College from home, which is what I'm doing right now. Okay, but I cannot be at home and be at West LA College at the same time. Okay, that's mutually exclusive. Okay, now so in the other words, if you find Thomas at home and also at West LA College at the same time, you're supposed to be super scared. Okay, so you may see a realm that is not human. I see dead people. Okay, so that's what mutually exclusive means. Now, on Monday, we will start working on problems in our book with 5.2. Okay, and 5.2 problems in the book, and also problems from my old tests. Okay, but before I let you go, I would like to write one formula that you need to memorize, and you will see this in my lesson 6. Okay, something called inclusion exclusion formula. I prefer this name. Our textbook called this general addition formula. I want you to memorize this first, okay? And then you will see that most of the time we don't use this formula. Okay, if I give you the Venn diagram, you don't need this formula. And on Monday when we start, we will use, we also get into what we call contingency table. Those are the type of questions we see a lot in our textbook. We also don't use this formula. Okay, we only use this formula if we don't have Venn diagram or contingency table. Now the formula says the following: probability of the union of two sets is equal to the probability of one event plus probability of the other event minus the probability of the intersection. Okay, the probability of union equals to the probability of A plus probability of B minus probability of the intersection. And implicitly, we already did apply this formula actually here without knowing that formula. Okay, probability of heart or union is the number of hearts plus a probability of heart or ace, right? The probability of heart plus probability of ace minus the probability of the intersection. Do you see that? Okay, but we don't need that formula if we can picture the situation. Okay, we don't need that formula if we can picture the situation. We did these questions without that formula, right? Do you notice that? Okay, so under what situation, Thomas, then we need to use that formula? If you don't have the Venn diagram, if you don't have the later on contingency table, then we will use this formula. That's something we will see on Monday. Okay, so on Monday, what I plan to do is, let me change this 5.2b. I'm sorry, A. I will do part B on Monday. On Monday, we will do union, intersection, and complement on Venn diagram. But at that time, we will use 3 circles, 3 groups, 3 sets. So far, we only have done 2, right? We will also apply this to contingency table. And we will also do if we have neither. Then I will continue to 5.3. Okay, so on Monday, then work on 5.3. Okay, 5.3 is not too hard. Of course, you need to think. Okay, but it's not too hard. What we had earlier today with this notation thing here is actually a lot harder. It requires your critical thinking. Okay, and you are right. If you get confused with the or and then you are actually majority of the what I see in class. Okay, what I encounter, a lot of students have difficulty there. That's why you need to study more. You may need to review this lesson again, but don't forget, watch my lesson 6, if possible, lesson 7. Okay, and if possible, read the book a little bit. Okay, this is where I will end today. See you then on Monday.